One of the great, if not the greatest opportunity of our time, at least in the physical economy. You know that we here at Pioneerland look also at the human economy, which is a whole different topic of civilizational rebuilding. But when it comes to the classic matter-based physical economy, one of the greatest opportunities is, of course, intelligence in space. Why? Because the world is scheduled to run into a major energy problem on the AGI build-out around 2028 is my prediction. Probably the resistance will already increase, no pun intended, in 2027, because already 7% of US energy is being spent on data centers, and that's going to double every year probably. So we have a problem starting next year, but then really getting into huge problems in 2028 and 2029 if the build out continues at the pace we see it now. And there's a lot of reasons to believe that the build out will continue at this pace, because there's no limit to the value intelligence can produce, and therefore there's no limit to the demand of build out. The solution to the energy problem is, of course, space. We all know that. That is why SpaceX is going public. That is why Tesla is now really focusing on chips and also on solar panels that are being prepared for space with SpaceX. That is why Amazon, the Google CEO, Microsoft, and of course Nvidia are all joining Elon in talking about orbital data centers. And now this fantasy, this theory is becoming very real. And our job here is to figure out as quickly as possible what are the exact economics, the exact timelines, and the exact technical problems and challenges and bottlenecks for the build out of massive orbital data centers, which then are the stepping stone to moon. And of course, the stepping stone to this crazy future that is going to be here full scale already in the 2030s of the Dyson swarms. So Dyson swarms are basically giant satellite swarms and over time spheres around a star, around the sun, that are being able to capture all the energy of the sun and turning it into intelligence. So that is all happening now, and here's a very interesting interview, not with
Obviously,
Elon, but this time with Jensen Huang, of course, the great CEO of Nvidia, and he is talking with the All-In team, getting interviewed about orbital data centers. And let's listen in what he has to say, and then
there's a lot of energy in space. The challenge, of course, is that cooling, you can't take advantage of conduction and convection. Exactly. And so you can only use radiation. And radiation requires very large surfaces. And so
let's stop here. I will explain this very quickly. If you cool, most people think, or a lot of people think, space is easy to cool because it's negative, what is it? It's like 0 Kelvin, negative 270 degrees Celsius or something. So 0 Kelvin or 1 Kelvin or something, basically it's very cold. But what people forget is coldness in vacuum doesn't help you. It doesn't cool you. It explodes you, but that's a pressure issue. But it doesn't cool you because you need some kind of connectivity. You know, vacuum bottles, why are they vacuum? Why are they're isolating the heat inside or the coldness inside? Because there's vacuum. So yeah, there might be a temperature differential between the outside and the inside, but if there's no connective tissue, connective atoms, connective molecules, the heat that basically the Brown's molecular movement makes all the little atoms and molecules run around in the space, and they bump into molecules that move a little less, that have less heat energy and movement energy, and then it dissipates because the slower moving molecules eat up the energy of the faster moving molecules. That is how heat dissipates. And that's how we cool GPUs on Earth, with water or with air or with metal. The problem is in space, that doesn't work because there's no air. You can't cool through these conventional means. So you need to cool through a specific physics paradigm which is radiation. You radiate out the heat, okay, into vacuum. That works, but you need massive amounts or much, much larger amounts of matter, of surface, there is a certain formula. You can look it up. Look up heat radiation formula, and you will see it. And therefore, in space, you will need very large radiator, probably aluminum-based radiators that radiate out that heat into space.
Now, that's not an impossible thing to solve, and there's a lot of space in space. But nonetheless, the expense is still quite there. Is there? We're going to go explore it. We're already there. We're already radiation hardened. We have CUDA in satellites around the world. They're doing image processing, AI imaging, and that kind of stuff ought to be done in space.
So here he's talking about radiation hardening, not to be confused with radiation, with heat radiation. So heat radiation is the problem, how you get it cooled, your GPUs, so they don't overheat in space. They need to have conductive materials with large surfaces outside space, and they radiate out the heat, and then they can take more heat and radiate it out, but the surfaces are very large. Now he's talking about radiation hardening, which means there's a lot of background radiation in space, which is all kinds of radioactive radiation. I don't even know which rays, but from the sun, from all kinds of sources. So you have strong radiation, which is very unhealthy for humans, but it's also problematic for GPUs because it interferes with the internal workings of a GPU, with the electrons floating around in the GPU, because these rays go through the CPU and distort it. So you have more errors and all kinds of stuff. You need to learn how to handle this. You can have radiation shielding, or you can have software correction for more errors. Bottom line is, NVIDIA has that part covered. That's
instead of sending all the data back here and do imaging down here, we ought to just do imaging out in space. And so there's a lot of things that we ought to do in space. And in the meantime, we're going to explore what does the architecture of data centers look like in space, and it'll take years. It's okay. I got plenty of time.
I wanted to double click on
obvious.
So that is interesting. He says it will take years, but I have plenty of time. And of course, the great Sawyer Merritt posted this via All In Pod, the podcast of these guys, Chamath and the crew. And Elon reposted this too. So Elon, he doesn't approve everything here, what Jensen says, but it seems like, yes, he thinks along the same lines. Now, what does it all mean? We have to understand on the orbital data center level, first of all, that's incredibly important. We already have convergence about predictions. Sam Altman famously said, who hates this whole thing, because Elon hates him. Elon has a monopoly on orbital data center pathways because he owns SpaceX or controls SpaceX. And if you want to have orbital data centers for the next 10 years, probably there will be no other option than Starship. And so OpenAI will have some problems because they're the enemy. Whereas Amazon and Microsoft and Nvidia will probably be able to use Starship to create their own orbital data centers. And Sam Altman, so he hates this whole thing because it puts him in a huge disadvantage. And he said famously, it is completely delusional. It will not happen this decade, which is a very interesting thing to say in 2026. So basically, Sam Altman was choosing his words very carefully. Basically, he was saying it's going to happen very soon in 5 years, but that's not this decade, right? So I think Sam is pushing it out a little bit. I think it will happen sooner at scale. I think it will happen in 2029 at scale. And we have to understand the two components that have to come together here is Starship reaching its commercial viability. Starship, the giant rocket, of course, that SpaceX is developing. I give you a very quick overview here. Starship is scheduled in version 3 to actually get to the next flight, or the first flight of V3. Here is the giant Starship, right? Beautiful, amazing marvel of engineering. This is Falcon. So Starship is scheduled for April to do this first next Gen V3 flight. And that comes very close to the commercial version. So maybe we have version 4, but between version 3 and 4, I think we're getting very close to having a reusable Starship. That is the critical singularity, space singularity inflection point, when the price per kilogram drops below $200 very quickly. That will be a function of Starship actually working, delivering payloads to orbit and returning and being reused very rapidly with these giant things here, with the chopsticks, the chopstick towers. All of this is happening now. The predictions are, and I'm not completely read up on it, so we are still doing some research. It's going to take another month or something to really get our hands around Starship and SpaceX and the IPO and everything. But my estimation is by end of 2027, we will be ready to get to drop that payload cost below $200 per kilogram. And that is the moment where you can build orbital data centers at scale. Now, the parallel trajectory, R&D trajectory, is the actual satellites. What is the exact size? Do we need tens of thousands or millions of these satellites? Are they very small? Do we need thousands of them? They're very large. If you want a gigawatt of compute in space, is this like 1,000 satellites? Is it 10? Is it 100,000? You know, these are the economics we have to figure out. And that will inform how large the radiator surface must be around each satellite, how many GPUs are in there, and what the solar array is around these satellites. So this is the big question that needs to be exactly figured out. The technology of radiators is extremely low tech. This is just matter, right? They just have to be made out of some matter, probably metal, probably aluminum. And so all these problems connected to it, by the way, the technological problems are extremely minimal if you would build it on Earth. The only problem is you need to transport that stuff into space, expand it, and the only real problem with that is the cost of the weight. But because Starship is coming, these equations will look much, much different from now. So these are the two trajectories that need to be married now. How long does it take to get these satellites ready to actually work at scale? And at the same time, how long does it take to bring down the cost for a kilogram to orbit below $200? The second question will be answered through Starship, will be the Starship trajectory, probably end of 2027. And that's conservative, could be faster. My personal take is that everyone except for Elon is overestimating the complexity of these satellites. Once you apply Elon Musk level insights here, you can fundamentally change the speed of development in that whole space, no pun intended. And you have great companies, for example, like StarCloud in Washington State, the great Galileo Russell covered that and had an interview with the founders. This is a cool company, and they're building all these satellites for space. And they are one of the companies that is really working hard on this. I do not think this is a major technological problem. And because of that, I think we will be in time. And because of that, I think everyone is overestimating how complicated it is. Now, Jensen said it will be years. He's definitely right about that. But will it be 2 years or 10 years? I think it will be much closer to 2 years than to 10 years. It will be something between 2 and 3 years, if you ask me. I think it will be 2027, 2028, 2029. In 2029, unless Starship messes up, which I don't think it will, we will have the ability on all technological trajectories to do multi-gigawatt data centers in space, orbital data centers. Most people got that wrong and would say it takes much longer. I do not think so for many reasons. You have 3 forcing functions. Number 1, Starship will be ready. Number 2, I think the satellites will be ready. Number 3, you run into an enormous energy problem on Earth for the build out of AGI. So that creates a push function and 2 pull functions. It's going to be hot. So let's see what happens. I just wanted to share this with you. Now you have seen what Sawyer shared here. Jensen Huang, coming out of GTC, bullish on orbital data centers, saying it takes multiple years. I say it takes 3 years. Let's see what happens. I hope that was interesting, and see you tomorrow.